Alright, I hope everyone have a good spring break. Due to the coronavirus, we're gonna go to online lecture today. So this is the first video I make in this online lecture series. So first of all, remember to wash your hand. Bring the hand sanitizer here. Okay. It's very important to stay healthy so that you can study well. Alright. I hope you guys don't forget what we covered before spring break. So I was trying to do a little bit of, I will try to do a little bit of review what happened before we take the spring break. So before we start in the spring break, we went through latches, right? So you remember that we have the SR latch and we had the D latch. I also put in the PowerPoint slide the R latch, but that's not really important. So when you study, focus on the SR and the D. So remember I was asking you, if you have, you know what's D latch, right? D latch is, you can also call it transparent latch. Other term is, okay, let me stand over here. Okay, you can call it transparent latch. Other term for it is D latch, delay latch, data latch. And the property of this latch is, okay, so this latch, I will not draw the circuit out, but technically the D latch is a, how can I say, D latch is an enable SR latch that have an enable SR latch that have one input S going to like one input S. Okay, so D will go to one input S, and D also hook into an inverter to create the opposite of S for R. Okay, that's the typical time. You can go back to SR latch to see and compare the structure, the logic circuit of D latch and an enable SR latch to see the similarity of them. Okay, but in general, you can always present a combinational circuit with a black box, right? We learn how to do black boxes above, and you label all the input and output. So D latch. So to represent D latch, you can just draw a black box like this. You represent the input, which is D, the data input. Another input is the enable input, okay? And you also have the output, which is Q, and the complementary output is Q naught, opposite of Q, okay? So I did not draw the truth table, but so remember why this one is called a transparent latch. This one is called transparent latch because when the input 1 enable is given into the enable pin, the latch becomes transparent. That means the output Q can see the input D, but after a certain delay, okay? So similarly, if you put 0 into the enable pin, then the latch becomes disabled. That means latch now is not transparent. Excuse me. Latch now become not transparent. That means the output Q cannot see the input D. Okay? So output Q cannot see the input D. Okay, so for example, if I give, can you guys see over here? Probably, let me check the camera. Let me check one real quick. Okay. Alright, I'm back. So so now, okay, this is an enable latch. What happens if I given the input D to be 0, alright? So Q will be 0 also, right? Now what if I change the input of D from 0 to 1? After a certain delay, Q will also change from 0 to 1. If I change it back to 0, and Q also change back to 0, right? And if I change it back to 1, Q also come to 1. Okay? So you can see the output Q can always see the input D after a certain delay, as long as the enable pin is 1. So what if the enable pin becomes 0? Okay. So now I will simulate the same scenario. So let's start with 0, okay. And I will assume that the initial previous state of this Q will be 0. Of course, it can be either 0 or 1, depending on what state that you set that in before. But if initially it's 0, right? If I change it from 0 to 1, this one still be 0. Doesn't change. If I change back to 0, it's still 0. If I change it back to 1, still 0. So you can see that when if you put a 0 for the enable pin of the D latch, the output Q is not sensitive. It cannot see what's going on, what's the change of the input D. Okay? It's always be the same. It's always be the previous state. So likewise, if the previous state of Q is 1, so it will keep always become 1, like it will not change. So that's the concept. Remember that I give you one example, and last week we went through a thought experiment. I mean, not last week, the week before spring break, we went through a thought experiment. Imagine if you connect two latches together. If you connect two D latches together, what is gonna happen? Okay, so I'm gonna erase all the yada 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 right here. Okay, so if I just connect the two latches together, okay, I have this pin, okay, I will call this pin D, okay. I also probe this pin out, and I will call it Y. I want to see that what is the signal going on in this location right here. And I will also probe this one, and I will call this one Q. Okay. And for the enable pin, what I'm gonna do is I'm gonna give it a variable called clock. Clock. And the shorthand for clock is CLK. I hope you guys can see that on the screen. So for the clock, for the first latch, okay, for the first latch, I'm gonna just feed the clock into the latch. For the second latch, I'm gonna leave the clock here. Now I'm gonna invert the clock. Okay, I'm gonna put an inverter right here, and a NOT gate inverter. That's two terms for it. I'm gonna invert the signal of the clock and feed that into the second latch. All right. So now remember, when we start this thought experiment, okay. So what we want to do is now, this is my problem statement, okay. Imagine if I push, I will write it over here. So imagine if we push, how can I push? If we push 1 0 1 0 1 0, so 1 0 1 0 1 0 series in this direction. So 1 then 0 then 1 then 0 then 1 0 in this direction into D. Okay. And we have an alternating clock. How the signal of Y and Q will change. How the signal of Y and Q will change based on each clock cycle. Alright, we're back. So now I just give you, basically remember this part. This axis is time, right? Then here I give you 4 different signals, okay? I color-coded them so the clock will be red, okay? And the clock will be red, while the input D will be green. So input D will be green. The intermediate signal Y, I will put it in brown color. Oops. And no need for circling. And the output Q will be blue. Alright. So, as I say, we know that the clock will be alternating, so I forgot to mention. Initially, all of the signal, let's assume they put all of them to 0. So D equals 0, Y is 0, Q is 0, clock also turn off. So before the start, can you guys see? Before the start, initially, like Q, so Q and Y, all of them is 0, right? Okay, all of them is 0. So now, when we start, okay, so let's assume from the start. When we start, the first thing I do is I turn on the first thing I'm gonna do is I turn on the D, okay? So I wanna start inputting, okay? And one thing to mention, I forgot to mention. If you see this line here, this black line here, and if you can see it on your screen, each frame representing for a clock cycle or a clock period, okay? One clock period is starting from when it goes back to 0. So from one cycle of 0 plus one cycle of 1. So the whole block right here, 0 and 1, is your one clock period or one clock cycle. Okay? So now the clock, at this time I didn't turn on the clock yet. Let's say the clock is still 0, okay? So clock is still 0, right? If clock is still 0, then D, okay? D is not, the D latch here is not transparent, right? It's not transparent. So because it's not transparent, the signal from D cannot be transmitted through to Y. So Y will be at this, sorry, it should be 0. Y should be at its original state or previous state. So up to this time, so we'll give up a little bit here, it's still 0, okay? It's still 0. So on, but for here, okay, clock is 0, Y is, this D latch, clock is 0, this D latch will receive a 1 right here, right, because there's an inverter. So this D latch here actually now is enabled, and because it is enabled, Q can see what's going on in Y. So Q should have the same signal with Y, right? But because Y is 0, Q is still 0. Okay, up to this point. Okay, so now, at this moment right here, so the clock turned on. Okay, clock turned on. What happened is when the clock turned on is now the first latch, and let me say something to clarify the difference between the two latch. I will call the first one master and the second one slave. So it's a master and slave. I mean, that's how they call it. I don't know why you can call AB, but they call it master and slave. So now the master becomes transparent, right? When the master becomes transparent, the Y signal will be equal to D signal, right? So signal Y up, go to 1, okay? Go to 1. However, clock equal 1, so master is transparent, but slave is not transparent, okay? So slave cannot see the signal of Y. So the output of the slave is still the same, okay? Now the next half of the clock cycle. Now up to here. Now we have the clock cycle go back to, now we have the clock go back down to 0, okay? The clock go back down to 0. At this point, the slave become transparent, and the master is not transparent, okay? Since the master is not transparent, it keeps the same state, so it does not change, okay? So keep the same state, does not change. But the slave, it can see the signal of Y because the slave becomes transparent. So now Q increase to 1. Okay. All right. Continue. When the clock goes back to 1 again, so slave become not transparent, master becomes transparent. Master becomes transparent, Y go down to 0 because Y can see what's going on in D. Okay. But Q keep the same. Okay. So next is clock go down to 0 again. So clock go down to 0, Y remain the same. Q can see what's going on in Y. So Q start going down. Okay. Up to 0. Now clock turn on back to 1. Okay. Clock turn on back to 1. Alright, so Y can see. Okay. And Q like this. Okay, the next one, clock go back to 0. So that's for Y. And for Q, just turn up to 1. So you can see the pattern here. Okay? Take a moment. See the pattern. If I have to completely fill out this entire table, it will be like this. Maybe I should edit this part out. Take more. Okay, so, alright. I didn't draw enough clock, but assuming the clock still flickering up and down. So now you can see the pattern. So this is if I keep going on throughout the whole thing. I want to ask you a question. So if you have a negative edge, D flip-flop, and if for every negative edge of the clock cycle, you start inputting or changing your value of your input, how long will it take for the output to sense that that change in the input? That means my question is, what is the delay time of the D flip-flop in total? And you can see in here, right? Each frame is one clock cycle, right? And my series is 1 0 1 0 1 0 and so on. And you can see that that 1 0 series doesn't start until one clock cycle after I change the input of D. Okay, so now you can see you can make some conclusion that the delay of your D flip-flop is one clock cycle or one clock period. Okay, so this will help with your design later. Okay, so next is we will go to a design exercise. Okay, so let's go through this design exercise. So assuming I want you to design a circuit, a 3-bit binary adder, but now I only give you one single full adder. Okay, you cannot use a bigger adder. Okay, I only give you single one full adder, and I allow you to use as many flip-flops as you want, and I also allow you to use clock. Okay, so how can I perform? How can I make that type circuit? So I start thinking. Instead of adding everything at once, you know, like what we usually do, we do our like propagation adder. We have triple carry or carry look ahead adder. Instead of doing that, now actually we only need one single full adder, and if we are able to just load in, you know, 2 single bits from A and B at a time, and then we can calculate the sum, and we can carry the C out into the next C in. We can imagine using something like that. So basically the requirement come back to, now we have to add a 3-bit A number, a 3-bit B number. So 3-bit A, I have A2, A1, A0. A 3-bit B, I have B2, B1, B0. To get a sum of S2, S1, S0 after 3 clock cycle. And I will explain why 3 clock cycle. Okay. So the central of our circuit will be our single bit adder, right? Now imagine if you have something called a memory block. Okay. Remember I told you guys before, you can actually build a registers, which means just a block to store memory and maybe to shift it. You can build some kind of memory block to store A2, A1, A0. Okay. You can also build a memory block to store B2, I'm sorry about this, B1 and B0. Okay, B2, B1, B0. And every time the clock cycle switch, every time a new clock cycle come in, you can start loading new bit into your full adder and spit out the result. And you can start storing the result in another memory block here. So what did we learn about memory? Okay, we just learned how to implement the first memory element, which is the D flip-flop. Okay, so this block right here, if I connect it to a D flip-flop, so I have a D and a Q and a clock. Okay, a D, a Q, and a clock. So this is the black box diagram for D flip-flop. Okay, so imagine all of the master and slave thing is inside. Okay, a D, a Q, and a clock. Okay, so similarly over here, I will just note it like this. Okay, D, D, Q, Q, D, Q, D, Q, D, Q, D, Q, clock, 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 clock. Okay. So now I can have some platform to maybe store my input, put my input through the adder, and collect my output. Okay, and I will show you how it works later. But we have a problem of carrying. So carrying still needs some memory, right? Yeah, you need to, for every single clock cycle, after you compute A and B single bit at a time, you need to put the carry out back into the carry in. But you cannot do that immediately, right? You need to wait for one cycle. Okay, now remember another thing. I asked you previously how long was the delay? How long was the delay for a D flip-flop? One clock cycle. So if you put a D flip-flop in here, it matches the requirement that we need, right? So instead of say some memory, I can erase this and I can put in a D flip-flop. And when you draw a D flip-flop, feel free to, flip it around like this. Make it D. And make this one Q. Okay, that means the data will be transmitted from here to here, input to output this way. I'll draw an arrow so you can see that easily. Okay. So now let's do a thought experiment with this adder that we have here. Okay. So now we'll start turning the clock. Okay. First clock cycle. What will happen? Think about the input first. Every single input here after one clock cycle will be shifted, right? One at a time, shifted. So A0 will jump into here. A1 will jump to here, so become A1. You see that? A2 will jump back to the place of A1. So A2 will jump into here. Okay. For B, it's the same thing. So B0 jump into here. B0. So B1 jump to here. So B1. Right? And B2 jump into here. B2. I erase this. So what happened here is when you can see that now we have the carry out one, right? So we have A0. Now your full adder will add this two numbers together. And I'm sorry, this is a B, not an A. Add these two numbers together and it will spit out S0. Okay. It's also spit out C0. Okay. Now you have C0. Okay. After one clock cycle, this C0, after another clock cycle come in. Okay. Another clock cycle come in, this C0 get from here, through here and back to Cn. C0 come in here. Okay. And this whole jumping thing happen again. So I have A2 is here, A1 is here. I will have B2 is here and B1 is here. Okay. Now I have my carry in, my A1, my B1, I add them together. Okay. Also, because of that clock cycle, that's S0. will jump to here, and S0 will jump to here. Okay. Now this will compute my S1. Okay. Then over here it gives me another CL, I will call it C1. Okay. Another clock cycle coming in. Okay, another clock cycle coming in. So let me do this first. Now S0 will jump over here. So this is S0. Okay. S1 jump over here. This one will become S1. This one will become S. This one nothing yet. So this one become S0. This become S1. Then the the new the C1 get pushed through. So C1 got updated over here. This one becomes C1. Okay, and because it's another clock cycle, so A2 jump into here, replace A1. B2 jump into here, replace B1. Okay. So now I perform my addition. I can have S2. Okay. All right. So now you can see that. Okay, if you turn on another clock cycle, if you turn on, and I can have my C2 out here too. Okay, so that's it. So if you prop the signal from maybe, actually I do not need this one right now. Then after 3 clock cycle, you turn off your clock, and you prop this 3 signal out. You can have your S2, S1. And that's 0, right? So now you just build yourself 3-bit binary adder. But different from what you learned before, this is not a parallel adder. This is a sequential adder. That means the signal come in 1 bit at a time, and come out 1 bit at a time. Your sequential adder is taking all of the bit at once and speed out all of the bits at once. Okay? So that's the difference. So next we will go to the PowerPoint slide. Then we will finish this D flip-flop to learn about all of the other type D flip-flop. Right. Welcome back everyone to the slide. So we went through what's flip-flop, right? There's basically right now we'll try to help you guys go through different type flip-flop. So we talked about a lot about the flip-flop, but there are also another thing called JK flip-flop and T flip-flop also. So we talked about the clock, so I'm just gonna skip through these pretty quickly. So clock basically is a signal that just turn on and off and on and off, okay? But the edge of the clock actually will provide some kind of trigger for your flip-flop to turn. Edge triggering. So now we're gonna talk about edge triggering. So you remember we went through that master and slave D flip-flop, which is a negative edge flip-flop. So on a clock, basically there's one block of time that your clock will turn on, right? So after it turn on, it will turn off. So the transition between off and on, okay, from off to on is called rising edge, and from on to up is called falling edge. Another term for that is from the rising edge is the positive edge, and the falling edge is the negative edge. Okay. Okay, so now we talk about D flip-flop. So D flip-flop, I would also call it a transparent flip-flop. Okay. So when it depends on your what's the clock signal, but when the clock signal trigger the flip-flop, the Q is your output, will be equal to your D input. Okay. This table right here show what is the behavior of the flip-flop when the clock is triggered. Okay. So there's two type of D flip-flop. There's a positive edge and a negative edge. We talk about this a lot for the positive edge. I mean the negative edge. I'm sorry. Uh, so the negative edge, basically you connect two D latches together, right? And we went through several examples to analyze this. Um, Another type is the positive edge. Okay, the positive edge, technically, if you look very carefully, what do you see here? You see two different, okay, you see two NAND gates, right? And the output of one NAND gate is connected to the input of another NAND gate. Now you go back to the SR latch lecture. Aha! You see the similarity there. So positive edge, the flip-flop is constructed by three different SR flip-flop. Okay, three different SR flip-flop, and the first two. And I think I can, how can I do a laser pointer in here? This is the pen, this is the highlighter. I do not know how to use a laser pointer, but maybe highlighter. Okay, so the first two, okay, this one and this one. So the first two SR latch is, so the purpose of that is process the input, is process and respond the external input, which is the D or data, and the clock, right? And the other, okay, the last latch, SR latch, is the output here. Okay, I mean it gives you the output Q. Okay, so that's on about the flip-flop. Let's go to, okay. So JK flip-flop. Okay, JK flip-flop. So it's a little bit different from D flip-flop. Okay, it have three input. D flip-flop have only two, which is data and clock. This one have two data input and one clock input. Okay, and so the key for JK flip-flop is if J is different from K, and the state of Q next will inherit or will be equal to the value of J. Okay, if J equal to K, then it will either hold or flip the value. So okay, so now you have so J, if J equals 0, K equals 0, or if J equal, let me do some highlight quickly. Okay, so no, okay, so if J and K are both equal 0, when the clock come, okay, if J and K are both equal 0, when the clock come to trigger, the value of Q will hold the same. Can you imagine? So if the previous state, okay, if the previous state of Q is 1, for example, and now you change J and K to 0, 0, that means when the next clock cycle come, the value of Q will be equal to 1 because it doesn't change, it holds. Okay, but for the case of 1, 1, okay, so if both J and K equal to 1, if both J and K equal to 1, then if the previous state of Q is 1, then the next state of Q will be flipped. That means Q will become 0 if I have J and K is 1, right? Okay, and also I have other input combination, which is I will highlight different color quickly. So for 0 and 1, or 1, 0, So the difference of this input combination is the state of Q doesn't depend on the previous state of Q. Okay, when you give the complementary input combination, the state of Q will be defined by a fixed number. So if you give J is 0, K is 1, you immediately fix Q to 0 on the next clock cycle. Always remember, clock cycle is important. Q won't express its state until the next clock cycle comes. And also with J equal 1, K equal 0, you can change the next state of Q to a hard value of 1. Okay, so how can you construct a JK flip-flop circuit? Basically, it's a D flip-flop, and you run a combinational circuit of an OR gate and 2 AND gate in front of it. Because of this circuit right here, how can you what is the Boolean algebra expression of D? Okay, what is the Boolean algebra expression of D? I can have D, okay, and I'm trying to draw with my mouse here, so it's pretty ugly, so excuse me on that. D will be equal to, so I have the first term, which is, so this is an OR gate, so it's the 2 terms, right? J and Q naught. Okay, this is my Q naught. Okay, and the next term will be, okay, I saw a K run through a NOT gate, so it will be K naught, and I saw Q going into that AND gate right there, so is K naught and Q. Okay, so from this Boolean algebra equation right here, you can actually understand more about that state or behavior table I put up there. So now imagine if you substitute J equal 1 and K equal 0. Now you can have, okay, J equal 1, K equal 0. So now the D expression can be simplified to D equal Q naught or Q, right? Q naught or Q is always equal to 1. Okay, you guys get that? That's why when you have J equal 1, Q equal 0, the next Q will be 1. Likewise, if you have J equal 0, K equal 1, D go to 0, so the next clock cycle, that D value equal 0 get pushed, that D equal 0 value get pushed through the D flip-flop, and Q will become 0. But when you have J and K both equal to 0, you simplify your D expression to D equal Q. Okay, so because of this, when you go to the next clock cycle, Q value doesn't change, and likewise, if you have J equal K equal 1, expression of D will become D equal Q naught. That means next clock cycle, Q will be flipped. You guys understand this? Okay, let's move on. Okay, next one. This one is way easier. So the JK flip-flop was the positive thing is, okay, you can decide when to, it can do more thing than just the D flip-flop, right? D flip-flop, technically all you can do is you can just transmit the data through when the clock cycle comes, and you can hold the data by not putting the clock into the D flip-flop. The JK flip-flop, it can decide what type of output you want to bring to the next state. Okay, so it's more complex there. The JK flip-flop, you can either make the output dependent on the previous state. Okay, you can either make the output dependent on the previous state of its own output, or you can hard code it the output. Okay, remember that. So if you have j equals 0 whole, j both jk equals 0 whole, jk both equal to 1 flip, or j equal 1 k equals 0, output is 1, j equals 0 k equal 1, output is 0. Okay, that's a lot of things to do. Sometimes you don't need that many things to work with. Maybe you only need to you only need that whole or flip function. Okay, so you don't care about, okay, I don't need to hardwire my output to some number, or like I don't need to give the output to 0 or 1. I always want to either flip or hold the value of Q. So what do I do? Okay, I make a T flip-flop. Okay, okay, I will explain why. Because T flip-flop technically is just a JK flip-flop, but you short wire the two input J and K into a T input. Okay, that means now you just ignore the case of what if J and K have different value. Okay, so of course now you see the behavior table of JK flip-flop. Technically I just take out the case that J and K are different, then you have the table for T flip-flop. Okay, now we go to direct input. We can so we talk about flip-flop. Actually the value of output in flip-flop will very much depending on its previous state, right? So sometimes you need a way to directly assign a value into the output of the flip-flop, or maybe you need to reset it. Okay, so it's good that you can hold the value, but sometimes you need to maybe reset it, then erase everything and start programming the flip-flop again. Okay, so this term is called like direct input. Like directly you want to force uh, like the flip-flop value go to like 0 or 1. Okay, so for example, for the positive edge the flip-flop. Okay, so normally you can have the remember you have the three SR latch, right? So you have it 1, okay, 2 and 3 here. Okay, what you can do is now you can make a reset state. Okay, that means you have a hard reset wire here. Okay, and you can run it to on 3 SR latch so that you can reset the value of Q, which is the output of this flip-flop, to 0. Or you can try to set it. Okay, you can set the value of that D flip-flop to 1. Okay, so this last slide is very easy since we already covered the others. So you can use flip-flop as a memory function. You can use it to store data. Remember that 3-bit binary adder that we did? We actually store data in the registers, right? We can use it to transfer data. So same thing. Every clock cycle we shift the data from our registers into the adder, then use the data storage at the output. Okay, and use is that also counter. Okay, so you can have some type of binary counter. Okay, so that should be it for our PowerPoint slide. I want you to remember that the flip-flop is one of your key elements to build memory. Okay, and with using some memory element, you can build a sequential circuit like this one we just did right here. And the next lecture we will go through. What's that called? The sequential circuit design. So okay, so thank you very much for attending this lecture online. Stay strong, study hard, and I will see you guys soon.